Good morning, everybody, and welcome to my talk with the weird title, The Hidden Rules of World-Class C++ Code. If you think that is indeed a weird title, a friendly reminder, you guys voted this talk into the conference, so I'm here because you want to hear something like this. My name is Boris, and I'm a long-term member of the Boost C++ community. Boost has nothing to do with my talk. I'm just introducing myself. Long-term member means that I have been active in Boost for about 15 years and thus did a lot of things there. My main field of activity has been, which I would describe as communication. So I'm usually trying to let people know outside the Boost community what the other guys inside the Boost community are working on. So I go to conferences, I give presentations, talk about Boost. I wrote a couple of books on the Boost libraries, which you can also read online, and I do trainings on the Boost libraries. So that is all about Boost, but as I said, this has nothing to do with my talk. This talk is about the hidden rules of world-class C++ code, and you might still wonder what that actually means, what this talk is about. So imagine you're coming across somebody's source code for the first time. You're looking at a project on GitHub, or you're looking at a project from one of your coworkers, and you do not only have a superficial interest, you're not doing a review for 5 minutes and then you forget about this talk again. You have a strong interest in that project. For example, because you will be the new maintainer of that project. So you have to really dive into the code and understand what the code is doing. So you will open a couple of files, you will look at header files, CPP files. You see classes, functions, templates, and all that stuff we are familiar with in C++. And while you browse the code, you will begin forming an opinion on whether you're looking at something which is good or which is bad. So if somebody asks you after 5 minutes or 10 minutes, how is it going? You will say something, looks pretty good. Or you will say something, oh my God, what a horrible mess. And most of the time you will say, obviously that. So if we dive into that process of how you form an opinion, we can maybe find out what it is that you're looking at when you come to the conclusion that you are looking at something good or you're looking at something bad. And we all know that there are a lot of rules in C++, and when you were here yesterday at the keynote Kate gave, you have seen her talking about all the rules we have in C++, all the guidelines, the best practices, and she talked about how complicated it can be. But if you think about how you form an opinion within 5-10 minutes, it still must be based on something. So you obviously look at a lot of details we are all familiar with. You're going to see whether somebody used smart pointers, you're going to see whether somebody used R-value references, you're going to see whether somebody used lambdas. But I could still use all of these things, and I could still create a horrible mess. And just because somebody uses all these latest and greatest features in his or her source code doesn't mean that this source code is good. That would be easy, right? We would just have a checklist next to our keyboard saying, just throw a smart pointer, an R-value reference, and a lambda function into your code, and everything is great. So I'm trying to explore the question in this talk, whether we can find a rule which somehow helps us to come up with a big picture of our code where other people would say, that looks good. And I'm not trying to find yet another rule after all the 100 rules we have already. I'm trying to find a rule which is somewhat more important when it comes to the bigger picture. So you have to give me the time to walk you through this talk to see whether we can actually get anywhere, which helps us. When I say I'm looking for a rule, I'm also not looking at something like keep it simple. I mean, we have a lot of very general rules in C++, but keep it simple is a rule which doesn't really help us. If you give me your source code and ask for feedback, and I tell you here where you use new and delete, you maybe should use a smart pointer, that is a very concrete advice. But if I tell you, you should maybe keep it simple, you have no idea what it means. And it's even worse because it seems as if I assume you did it intentionally complicated. You didn't even know to keep it simple from the beginning. and I've never seen a developer who told me I always try to make my things as complicated as possible. And when you tell him, hey, there's this rule, keep it simple, he says, thank you very much. Now I know what I need to do to improve my code. So I'm looking for something which is a bit more concrete, so that there are action points, something we can do to help us create better code. So throughout this talk, I will actually show you a lot of C++ code, though this is not an abstract talk. There's a lot of code to look at. And all the code you will see will be based on this factory method pattern. I picked this pattern because I believe a lot of people here in the room are familiar with it. And those who aren't familiar will understand easily in 1 and 2 minutes what that diagram actually does. So what do we see here? We see here 2 class hierarchies, one on the left side and one on the right side. Both class hierarchies consist of 3 classes. There's a base class called connection on the left side and a base class called connection factory on the right side. There are 2 classes derived from each base class, TCP connection on the left side and UDP connection. And on the right side, TCP connection factory and UDP connection factory. The connection class hierarchy on the left side has classes with one member function called send. And on the right side, the connection factories, they have a member function called make. And the idea is obviously that when you have a TCP connection factory and you call make, that make function returns you a TCP connection. And when you call make on the UDP connection factory, well, you get a UDP connection. Pretty straightforward. Now, if you search for factory method pattern on the internet and try to see what other people say about it, you can find a lot of information because that is a design pattern a lot of people are familiar with. So I just copy and pasted some random quotes I came across to see what other people say. What are the reasons somebody might want to use this design pattern in code? So somewhere I found the quote which says, places that need an implementation of the connection do not need to know how to construct one. So what does it mean? When we need to use a connection at some point in our code, we don't need to figure out ourselves how to create that object. Maybe it's rather complicated to create a TCP connection object. So instead, we can just go to a connection factory and ask the connection factory to create that object for us. So the connection factory knows how to do that. It knows how to maybe do a lot of complicated things. But we just call make on the connection factory, and we get our connection object. Is there a reason why we would want to use this design pattern? Sure. Seems like a very nice benefit. So we could maybe wrap this up as the delegation benefit. We can delegate creating a connection to someone else who does it for us and gives us the object back we are interested in. Now I found another quote somewhere else on the internet. Somebody wrote that this design pattern provides a simple way of extending the family of connections with minor changes in application. So what does that mean? We can easily extend our class hierarchy with connections. That is the class hierarchy on the left side, which so far has a TCP and a UDP connection. And if we want to, we can easily extend our program and derive another class from our connection-based class. So we can wrap this up as that our program becomes easily extensible with that design pattern. After all, we have a class hierarchy. We can link as many new classes in this class hierarchy as we like without having to change any of the existing code. So the first quote was about delegation, a benefit this design pattern provides. The second quote is about extensibility. All good so far. Let's look at the third quote. Somebody wrote, delegate to a subclass the creation of a connection that can vary based on application needs. And what the hell does that mean again? Well, it also refers a little bit to delegation. After all, it even says delegate. It also talks about subclass again, so it has something to do with extensibility. But it also talks about the creation of a connection. So that refers now not to the left class hierarchy, but to the right class hierarchy, to the class hierarchy with the connection factories. These are the classes that deal with creation of a connection. So we can maybe wrap this up that we can use this design pattern not only to extend our program easily by adding connection classes, but also by adding connection factories. Again, that's very obvious to all of us. After all, we have also on the right side a class hierarchy with a couple of classes. We can easily come up with a new connection factory and add that class to the class hierarchy on the right side. So this isn't really anything new. This quote is also about extensibility. We have one last quote, which is about allows a connection to be requested without inextricable coupling to the act of creation. So this quote refers to the fact that when we call make on a connection factory, the connection factory can actually be implemented in a way that a connection object is not created when make is called, but that the connection object is maybe already created when the constructor of the connection factory was called. Because this design pattern is based on classes, and because my connection factories are based on classes, I have the chance to, for example, pre-allocate a pool of connections in my constructor of the connection factory. And when then later somebody calls make, I will just take one object of that pool and return it. So this quote is about that I have a chance of decoupling the act of creating a connection from the act of requesting, right? The quote even says, act of creation. Act of creation is something you could put into the constructor or you could put into the make function, depending on how you want to implement your connection factory. So the quotes we find give us the idea that there are a couple of benefits, a couple of reasons to use this design pattern, and we can wrap them up as delegation, extensibility, and decoupling the act of requesting from the act of creating. All right, so let's finally look at some C++ code. How would we write now the code? And my guess is most people, not only in this room, but most people in the C++ community would write something like this. And when we look at this, it seems to be reasonable, right? That is what, regarding our intention, feels like the code should look like. So we have on the left side 3 classes, connection, TCP connection, and UDP connection. And we have on the right side 3 classes, connection factory, TCP connection factory, UDP connection factory. 2 classes are derived from a base class, so connection and connection factory are our base classes again. We see again our send and our make functions as we use inheritance. Send and make are virtual. Connection and connection factory are abstract classes. We see that send and make are pure virtual. And we see that in the derived classes, these functions have been implemented. So I have a very simple implementation here. For my connection classes on the left side, I just take the string which is passed to send and I just write it to std_cout. And on the right side, I've implemented my make functions that they simply instantiate a connection and return that object. Now you know that, of course, these functions don't return an object. They return a pointer to the base class, but I don't need to explain this to you. We all know that is just how it works. So I call this the traditional implementation, and I will refer to this implementation during my talk again and again. So when I say traditional implementation, think of this C++ code you see here. Now, how would we use this code now in a program? Here's a main function and a send function. What do I do in the main function? I'm looking at the command line options, whether anybody starts my program with the command line option TCP. So if somebody types program name space TCP and then presses enter, then I will create a TCP connection factory in main. Otherwise, I will create a UDP connection factory. And whatever connection factory I will have, I will just pass it on to my send function. The send function takes the connection factory, calls make, gets a connection object, and then calls send on the object just to write a string through that connection object somewhere else. Now, when we look at this code, we all immediately know that there's something we can improve. We are all familiar with modern C++, and we all know we are not supposed to use new and delete anymore ourselves. So let's just quickly change this code and get rid of all these raw pointers and use smart pointers where we are supposed to do so. So I change my class hierarchy here on the right side. My connection factories don't return a raw pointer to a connection anymore, but a unique pointer. The make functions here also now obviously don't use new anymore to create connection objects. I use these little helper functions from the standard library. And I adapt the rest of my program so that all those new and deletes are gone. Again, I assume I don't need to explain much here. There are a lot of other talks at this and other conferences which talk about how that works. So now we have an implementation which we could call modern C++ based. During my talk, I will still refer to all of this as the traditional implementation because not much really changed, right? I still have my class hierarchies here. I just have now introduced some smart pointers. Now, somebody here might say, for this little program, using a design pattern is a complete overkill, right? I mean, why do we have all these connection factories if all we need is just to instantiate a TCP connection when we need to and to instantiate another connection when we need to? So we could, of course, throw away all these class hierarchies and get rid of the design pattern and come up with some code which is much shorter. But the idea of this talk is not how to write this program with as little code as possible. The idea of this talk is to explore whether we can find an alternative implementation for that traditional implementation we have seen. So yeah, that is doable, but that is not the point of this talk. So we have now seen this traditional implementation, and maybe a lot of people say, yeah, we're kind of done. Talk is over. Have lunch. But I would try to find now something else. I would try to find now some kind of alternative implementation for what we have just seen. And I start by breaking down the factory method pattern to see what its advantages are. Not only from a point of view of the design pattern, but also from a point of view of the traditional implementation we have just seen. So when we think of all the code we have just looked at, let's see what the benefits of this code are. So we came already across the benefit of delegation. That was also one of the quotes I found somewhere on the internet. We said, if we use this design pattern in our code, we can easily delegate creating connection objects to someone else, to those connection factories. And if we look at our traditional implementation and at how we use it, we see that there is indeed that benefit visible in our code. If you want to have a connection object here in our send function, all you need to do is call make on the connection factory, and you don't need to worry about how complicated it is to create that connection object. So there is indeed a benefit of delegation. But if you think about it, if you write some C++ code and you want to benefit from delegation, you don't really need to go to the factory method pattern, right? If all you need is delegation, then all you need is a simple freestanding global function. The function doesn't need to be attached to something like a connection factory. You only want delegation. You only want someone else to do the work for you. Well, then all you need at that point is a function. There are more reasons why we said we want to use the factory method pattern. We also said the program becomes easily extensible. And we said, yeah, that's true. We have these class hierarchies, and we can easily add more classes and derive these classes from the base class. But if we start again at functions, which we just said, that's all what we need for delegation. And if you think about extensibility, do we really need to introduce anything else to our program if we have already functions? If I have a program full of functions and I want to extend my program, well, I can add another function. So if I want to benefit from delegation and extensibility, I don't need all of these things the factory method pattern promises to me. If I only need delegation and extensibility, all I need is functions. So far. There are, of course, more benefits in that design pattern. We saw that we can also easily reuse code. We have this little send function here, and we can pass any connection factory to that send function, and the send function will just happily accept the parameter and call make and do whatever it needs to do. Now, when it comes to code reuse, we are, of course, experts in C++. There's something else we can use. Again, we don't need to do all those things the factory method pattern promises us and requires us to do. When it comes to code reuse, we can just use templates. So for delegation, we said we only need functions. For extensibility, we still only need functions. When we want to benefit from code reuse, we need templates. There was this other quote on the third slide where somebody said, if you use the factory method pattern, you can decouple the act of creation from the act of requesting an object. And if that is a benefit we also want to have in our code, we have to give up functions. We have to use a class, because we said if we have a class, we have actually the possibility to decouple the act of creation from the act of requesting. The act of requesting refers to calling make on the connection factory. That is when we want to get a connection object. But if the connection factory wants to have a chance to put the act of creating those objects somewhere else, we need to provide an opportunity to do this, and that is something we can do if we use a class, because then we have a constructor and the connection factory can pre-allocate those connection objects before somebody calls make later. So if we want to benefit from this ability, from what I call the benefit of decoupling, then we would need to use a class again. That's fine, but at that point we still need to use a class hierarchy. We still have a reason to embed our classes in something bigger. So we have a couple of benefits which this design pattern provides us and which we also find in the traditional implementation again. That is delegation, extensibility, code reuse, decoupling. Also, it's a very specific use case of decoupling. It's not what we otherwise think of when somebody says decoupling. This is really only about decoupling the act of creation from the act of requesting. And when I break this down and think about how I could benefit from all those things differently in code, I could say, well, for delegation, I just need a function. If I want to extend my program, I still only need a function. If I want to reuse code, I need a template. And if I want to benefit from that very specific case of decoupling, I would use a class again. Now, there's one more benefit that traditional implementation provides us. And that is what I call a common interface variable here. If you look at that main function, we have a variable called conFactory. This is a variable I can assign to either a TCP connection factory or a UDP connection factory. After all, the variable is created first, and then I evaluate the command line parameter. So I decide later at runtime whether I want to put a TCP connection factory in that variable or a UDP connection factory. Now, we all know it's not really the object which is put into that variable, it's just a pointer. But I have the ability to create a variable which can somehow store different things. So if somebody says, hey, that's something I need in my program, and I need it here, then I need to introduce my class hierarchies again, right? I will ignore this for now. We will come back to this later. We will now start putting an alternative implementation together based on what we have just seen in the overview. So I will start with functions. We said if we want to benefit from delegation, all we need is functions. So there's no code highlighted here because this is all completely new. We see some classes which we have seen before. On the left side at the top, we have the TCP connection class and the UDP connection class. I mean, this is still something we want to work with. We still want to have some connections in our code. But then below these classes, we see two functions called make TCP connection and make UDP connection. So these two functions are now our new connection factories. We said we only want to benefit from delegation. We want someone else to do the work for us. So if I have a function called make TCP connection, I can just call this function from anywhere else in my program, and this function gives me a TCP connection. Now, if I use functions in my program, I do not only benefit from delegation, I also benefit from extendability. We have seen in the overview that if we want to benefit from extendability, we still only need functions. And it is true, if I have two functions, make TCP connection and make UDP connection, I can just add another function and easily extend my program. So if I need a HTTP connection in my program, I would just define a new function, make HTTP connection. So to use these connection factories in the rest of my program, which we see now here on the right side, I have to change my send function a little bit. The send function was expecting a pointer to a base class before. Now I turn the send function into a template, and I call the send function here in my main function, and I pass these connection factories, which are now functions, to send. And because send is a template, it can just take whatever you pass. It will invoke the connection factory. After all, it's just a function, and the connection factory still returns a connection object, and you can still call send on that object. So we actually have a little bit more here. We do not only have functions for delegation and extensibility, we already have a template too, a template for code reuse. All right. So we have already 3 of the 4 or 5 benefits which we have identified so far. 4 were on my overview, and the 5th one, that was a benefit with this common interface variable, which I have kind of ignored for now. So I have 3 benefits, and if somebody says now, hey, I want to benefit also from this decoupling thing. I want my connection factories to pre-allocate connection objects, so that when somebody calls make, I can just return an object immediately without having to construct it on demand. Then we have to change the code, and we have to introduce classes again for the connection factories. So my make blah 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 connection functions are gone. I have again a TCP connection factory class and a UDP connection factory class. My make functions are back. And I have to change the rest of the code because I now need, obviously, to instantiate the class. I need to pass the class to my send function, and my send function needs to call make again on these connection objects, connection factories. All right, I guess pretty straightforward. What's again important to understand that at this point, I could change the implementation of my connection factories in a way that I add a constructor, that the constructor allocates the connection object, and that make later simply returns that object. I wish I would have done this here because it would be more obvious, but you're always running out of space on these PowerPoint slides. All right, so which are the benefits we have now? We have delegation, we have extendability, we have code reuse, and we can also benefit from this thing called decoupling. All right, that's all good so far. But there was this 5th benefit, this variable, which I called common interface variable, which could hold either a TCP connection factory or a UDP connection factory. If somebody tells me I need to be able to create this variable in code so I could pass some other object later to that variable, and that this other object is related on some other type, then the question is, how can I get this done? And when we think of the variable we have seen before, this variable I called common interface variable, then all of this was possible because our classes were all derived from one base class. And because our classes were part of one class hierarchy, the classes had a common interface. Because classes were derived from one base class. They all had to implement the same interface. And because there was a common interface, we could create a common interface variable. So what I'm trying to do now, I'm trying to create a common interface again. I have my TCP connection factories here on the right side, which have this make function. If I go one slide back, here at this point, the TCP connection factory returns a TCP connection object for make, and the UDP connection factory returns a UDP connection object for make, which sounds all very reasonable. But if I want to use now this common interface variable, I need to align these interfaces somehow. I need to make sure that these connection factories have a common interface again. So how do I do this? I introduce a class hierarchy again for now. So on the right side, you see my make functions. And in order to make sure that these two classes here on the right side have a common interface, I will change those classes, I will change those functions and make them return a unique pointer to a connection again. That means I need to introduce my connection class again here in my program on the left side. So for now, unfortunately, my connection classes on the left side are all part of a class hierarchy again. Again, I have my virtual functions here, but all of this allows me to create a common interface for my connection factories. All right, that's good. So these make functions here have now the very same signature. How does this help us now? What can we do now next? Can we create now a variable which can hold either a TCP connection factory or a UDP connection factory? Will I make one more change to get back then to our main function? I'm renaming the make functions here. I'm replacing them with a function operator. So there's no other change here. I'm just getting rid of make, and I'm using the function operator here. We still have a common interface. It's still the same function signature. And how does this help us now? Maybe you have already an idea. Now I can use a class from the standard library called Boost.Function to create a variable which I call common interface variable, because I can store anything in that factory variable which has that interface. So I have a variable here, factory, which is based on Boost.Function. Boost.Function is a template, so I need to specify something here, the template parameter. And I say, in that factory variable, in that common interface variable, I want to be able to store anything which is callable, which can be invoked with no arguments, and which returns a unique pointer to a connection. Now, as it happens to be the case, this is exactly the interface my two connection factories now have. So now I have my common interface variable again, and I can evaluate my command line options, and I can decide later in my program whether I want to store a TCP connection factory or a UDP connection factory in that variable. So the important point at this slide is that I have the benefit again, which the traditional implementation provided me through those class hierarchies. So in this case, if I go one slide back, if you look again at our connection factories, these connection factories are not part of a class hierarchy. Those functions here on the right, well, they're not called make anymore. There are no function operators, but those functions, they are not virtual. We have two separate independent classes, and we can still store them dynamically at runtime in one variable. That was everything I could also do before with my traditional implementation. That is something I can now still do with an alternative implementation, which is based on this little helper class Boost.Function. Now there are still two things I don't like. First, I had to introduce my class hierarchy again for the left side of my program. I go back one slide. My connection classes, they are again all derived from one base class. That was something I needed to do to come up with a common interface on the right side. And I also had to get rid of my make function. It had such a nice name. Now it's this weird function operator. So let's see whether I can do something about this. So first, I get rid of my class hierarchy again on the left side. So I want my TCP connection class and my UDP connection class, again, to be independent entities, not derived from a base class. Then, of course, I need to adapt my functions in the connection factories. They cannot return a pointer anymore to some base type. There is no base type anymore. So my TCP connection factory returns a TCP connection object. My UDP connection factory returns a UDP connection object. So that's all good. That looks even better than it does before, but now I have a problem. I still have my common interface variable here on the right side. And I mean, what do I put in here? What do I tell this variable that I can still store a TCP connection factory or a UDP connection factory later in that variable? It's a good moment to drink some water. So is there something I can do here without introducing all these class hierarchies back in my code? And I told you that I'm a long-term member of Boost, so we have, of course, to come across one Boost library at least in this talk. There's a library called Boost Type Erasure which can help us. And what you will see now looks probably a bit weird if you have not played around much with type erasure. And you can make this code now work without having to go back and introduce a class hierarchy. So if you look at this factory variable down here in my main function, it has a template parameter which says anything can be stored in that variable which can be invoked and which returns a connection. Now if I go back one slide, I know as a programmer that I have two connections here. I have a TCP connection and I have a UDP connection. But these are separate classes, so I somehow have to tell the compiler, well, these two things are connections, and I want to be able to store something in my variable down here in main, and if that something can be invoked and returns a connection, and I know what connection means, then this should work. Now, one way of telling the compiler how all of this is related to each other is using a class hierarchy. But as I said, I'm looking for some alternative implementation. And the alternative implementation I can create thanks to that Boost library, Boost Type Erasure. So as this is a Boost library, the code looks maybe a bit more complicated than it should be. But to walk you quickly through that highlighted code, I'm creating here a new type called connection. So I'm trying to tell the compiler what a connection is. And I'm trying to tell the compiler that a connection is anything which has a send function. I mean, if I go back one slide, this is exactly how my TCP connection and UDP connection classes look like. They have a send function, and because they have a send function, these things are connections. So I tell the compiler a connection has a send function, and here for my program, I'm also telling the compiler that a connection is copy constructible. So how do I do this? Well, I have to use a little bit glue code from Boost Type Erasure. I have to use a macro called Boost Type Erasure member. The first parameter is just a name for a requirement. I call this requirement has send to specify that I use this requirement later to tell the compiler that my connection must have a send function. So the first parameter is just a name. You could call it anything you like. The second parameter to this macro is the name of the actual member function. So in my case, the member function is called send, so I have to pass send here. So once I have defined this requirement, I can use it later here in my type Boost Type Erasure any. So Boost Type Erasure any kind of means a connection is anything which means the following requirements. And then you pass in a list of requirements. In order to pass in a list of requirements, you have to use another weird class called Boost.MPL vector, but let's ignore that for now. And with Boost.MPL vector, I can pass in all those requirements which I want to use to tell the compiler that this is our connection. So the first requirement is just to tell the compiler our connection has a send function. And the send function has not only the name send, it has also a specific signature, which is in this case void const char star. So if I go back one slide, this is exactly how my send functions look like in my two connection classes. So because I copy somewhere in my program connection objects around, I also say a connection has to be copy constructible, and I can refer to some kind of keyword which is provided by that library. So I use something called Boost type erasure copy constructible. And that's it. Now I can use this type connection and put it here into that template parameter which I passed to Boost.Function. Now I can store anything in Boost.Function which is invocable and which returns a connection according to those requirements I have just specified. And again, if I go back one slide, if I look at my connection classes here on the left top, they do meet the requirements I just wrote down. So as crazy as this code looks like when you come across this Boost type erasure library for the first time, all of this compiles and works. So at that point, I have no class hierarchy anymore, but I still have this weird function operator in my connection factories. In the beginning, I had this nice function called make. So let's see whether we can go back and introduce a more readable function name here. Okay, I always forget these pictures, but then they're not that important. So I want to write again code which looks like this. I want to call make on my connection factory because I find this, for whatever reasons, more readable, which means I need to change my connection factories. I need to replace those function operator and use make again. All right, so if you remember, I had introduced this function operator because that allowed me to use Boost.Function here in my main function. Now, if I get rid of my function operator and I use make now, I can't use Boost.Function anymore because my connection factories, they are not callable anymore. So I have to use something else. I start a little bit like I started before. I just use a type here for my common interface variable which doesn't exist yet. So I'm saying I want to be able to store in my factory variable a connection factory. This is a variable to store a connection factory. But I need to tell the compiler again what a connection factory is. One way to do this is, again, introduce a class hierarchy. But we have just seen that there's another way to tell the compiler what something is. So now I'm using Boost type erasure again to tell the compiler what a connection factory looks like. So this is the highlighted code you see here. Looks kind of similar to everything which we see above, except that I need, of course, to specify now different requirements. So I tell the compiler a connection factory is anything which has a make function which returns a connection which I've defined up there. That is what I defined before with Boost type erasure. Our connection factory also needs to be copy constructible. And our connection factory has to meet a requirement which is called Boost type erasure relaxed. What does that mean? Where does this Boost type erasure relaxed come from? If I go one slide back again, Boost type erasure relaxed allows me to create a connection factory variable without having to initialize this variable immediately. So if I don't use relaxed, the code wouldn't compile. The compiler would tell me, you have to put a connection factory object into that variable right away. You can't create an empty variable and then later decide which connection factory object you want to put into it. So that's the reason why I add this requirement, Boost type erasure relaxed. So that way I have told the compiler how my connection factories look like, what kind of requirements they have to meet, and all of this code suddenly compiles. So now I ended up with an entirely different implementation of my design pattern, which still provides me all the benefits the traditional implementation provided me. So I have delegation, I have extendability, I have code reuse, I have decoupling, act of creation and act of requesting, and I can create these common interface variables. All right, what now? I have two different ways of implementing this program. Can we say that one way is better than the other? If you remember, this talk has something to do with world-class C++ code and not just with let's come up with some arbitrary implementations. So if we think about what we have been doing so far while playing around with these programs, we used various language features. In the beginning, we used runtime polymorphism with all those class hierarchies. And later, we used functions, classes, templates, type erasures. We used all those things because we wanted to benefit from a couple of different things. We wanted to benefit from delegation, from decoupling, from code reuse, and so on. Oh, that is unfortunate. Okay, sorry. So if we look at all the language features we used now, we see that runtime polymorphism here on the left side promises us delegation, decoupling, code reuse, common interface variables. And if we look at all those other language features we see here on the right, we get the same benefits. So we still have two different ways of implementing everything. And it seems like that we are revealing our intentions in both ways equally well. So is there a way that we can pick one way over the other? And you can come up with a lot of reasons now. I mean, there are a lot of arguments for one implementation or the other. Very simple one, if I just go back to the previous slide, is that there are no virtual functions anymore, right? And usually C++ developers interested in performance say, hey, if I can get away with non-virtual functions, I prefer this. But in my experience, this is an argument which, for whatever reason, doesn't work. It is too weak. So when people have created all their class hierarchies and you tell them you can come up with an alternative implementation without those virtual functions, they say, yeah, but I'm not going to change my class hierarchies. This is how I've always done it, and just because they are virtual functions doesn't really matter. So I've been trying to look at all the arguments there are, and instead of throwing now a lot of arguments to you which are all weak, I'm just going for one argument. The one which I think is the strongest argument why you would want to prefer one implementation over the other. And the strongest argument, at least in my opinion, is that it is all about communication. So the way you write code is that you think about what you're trying to communicate. In a way, I'm referring to the talk Kate gave yesterday. She was also talking about and not only all those rules, which there are, but about what is good code, and that good code should be self-explanatory and that it should express the intentions of the developer who was writing the code. So when it comes to all that code we have just seen, when it comes to picking one implementation over the other, I would say we have to think about what we are trying to communicate and how we are communicating. So again, when I look at all the language features we have here, and we think about what we are communicating, it doesn't really help us because we are communicating the same things, right? Whether we use runtime polymorphism or everything else, we are communicating that we want to benefit from a couple of things like delegation, decoupling, whatever else is written down on this slide. So there's still two ways of communicating the same things. So can we come up with some other rules which helps us picking one implementation over the other? So and I would say that when it comes to communicating and picking a language feature from that circle we have just seen, we have to think about what the defining use cases are for the various language features. What are the use cases where we have to use a language feature, where we cannot use any other language feature? If we restrict ourselves to those use cases, if we use a language feature only in a use case where we have to use it, we are communicating to somebody else who's reading our source code. Or maybe we are communicating with our future self, just like Kate said. I mean, we are the one who is maybe reading our source code again in a couple of months, trying to understand what we thought back then. If we are using language features in those use cases only where they have to be used, then we are communicating to the reader that you find yourself in such a use case. There's a good reason why that language feature has been used. And I'm telling you that if you become the new maintainer of that project, that is how I started the talk, right? We are having a strong interest in that project because maybe we become the new maintainer. I'm telling you that this language feature has been used for the right reason. This is the use case where I have to use a language feature. So don't start wondering about it when you become the new maintainer, whether you can change the code arbitrarily, whether you can throw away that language feature. Because you will have to make changes, obviously, to the code. Requirements change, life goes on. But if I can reveal my intentions through the code to you, that you understand why language features have been used in different places of my code, then you will hopefully understand what you can easily change and where you maybe need to talk to other people first to find out whether those requirements still hold on. Now, if we come back to my example with the two different implementations, the traditional implementation and this new implementation I came up with, does this rule help us somehow? So I said that we are supposed to use language features only in those defining use cases where we have to use them. So I have just proven to you that we don't need to use runtime polymorphism. We don't need to use class hierarchies or virtual functions. We can actually get away with an alternative implementation. So I could argue that this is not a use case where you have to use runtime polymorphism. But then you could turn it around and tell me, well, if you had started with functions, classes, templates, and Boost and type erasure, I could have created another implementation based on runtime polymorphism. So I could argue this is not a defining use case either for everything else you used, right? So you could obviously always replace the one implementation with the other one, and it just comes down to where you start and where you end up with. So if you think about what those defining use cases have to be, we have to go one step further. Skip this slide, it's not that important. So when I think of defining use cases, I think of something which has a very small scope. It reminds me of another rule we have in C++, that is the rule that when you create variables, you're supposed to minimize their scope. You don't put variables into the global scope because you would be communicating to someone that this variable needs to be accessed by your entire program. If you know you need to access a variable only in a class, you put that variable into the class to communicate that variable will only be used by this class. And if you want to communicate that a variable is only used in a function, you put this variable only in that function. You minimize scope. I think that is a rule we are all familiar with. So if you think about defining use cases, we are also supposed to minimize scope, to create use cases which are local in code. So when I look back here at my common interface variable, that is my variable factory here in my main function, and I want to be able to use such a variable which can hold different connection factories, then I'm trying to come up with a solution which tells the reader that at this point in my program, I need type erasure. My intention at this point in the program is to be able to store different objects of different types. So this is my local use case, my attempt to minimize scope. There's no reason to jump to a completely different part in my program, namely to my connection factories here on the left side and to my connection classes, and throw all these class hierarchies at them. Yes, that is an implementation which works, but that is not an implementation where I'm trying to minimize the scope. So my argument is that this, what we see here, is a better implementation because I'm communicating with somebody else through code more clearly and precisely. I'm communicating that at that point in my program, here in my main function, I want to use a common interface variable. If you read other parts of the code, if you look at the connection classes or at the connection factories, you shouldn't worry about whether I need to use a common interface variable somewhere else. This is also known as separation of concerns, something you maybe came across before, something you can look up on Wikipedia. Right? You don't want to confuse the person reading your code when he's looking at the connection classes or the connection factories with something he doesn't need to worry about. So I'm trying to pick language features which don't pollute the rest of my program. Language features which I have to use at some point because there's no other way, or at least no other way I know of, to create this common interface variable. But if I can use a language feature which is really only impacting this little part of the code, then this is something I prefer about another language feature like runtime polymorphism, like class hierarchies, even so they would do the same things. So when I come across code, and maybe you also came across code a lot, which is based on class hierarchies and virtual functions, I always ask myself, has this language feature been used in a defining use case? Is this a use case where I have to use runtime polymorphism, where I have to use all those class hierarchies with virtual functions? And there are, of course, use cases where we have to do so. That is the slide I just skipped because I'm running out of time. So if you think about it, there's a reason why we can use runtime polymorphism in C++, and there are use cases where it is perfectly fine to go for this implementation. But if I look at this example I just went through, I don't have that defining use case for runtime polymorphism. I can use other languages, other language features, which help me to minimize that scope, where I can communicate more clearly and precisely to someone that I need to do something here, my intention to do something here at this point of the program is this, and you only need to worry about this here at this point and not at other parts in the code. So when I see code where language features are used in such a way that I find myself in these defining use cases, so that somebody communicates clearly to me what his or her intentions are at that point in the program, then these are the moments where I think it could be that I'm looking at code which is world-class. I have one more slide, which I added to help me back up my arguments. Doesn't matter that much. There are a couple of references to other people and to some documents on the internet. Sean has given a lot of talks, and there's one talk he has given a while ago about better code, runtime polymorphism. We also talks about the goal of not using inheritance. There's also a reference to the Boost type erasure homepage, which says that there are two distinct kinds of polymorphism. So every time somebody thinks I would just go to use runtime polymorphism with all these class hierarchies because that feels like it is intuitively the right solution. This is a reminder that there are two different kinds of polymorphism, and runtime polymorphism and virtual functions is just one kind. It's not better or worse than the other, it's just one kind, and you pick the kind depending on what you want to communicate and depending on what your defining use case is. That being said, I'm at the end of my presentation. If you still wonder how the heck did all this code actually compile with Boost type erasure, you can find all the examples on GitHub. So you can go there yourself and actually try to compile this just to make sure I didn't say any nonsense here. So yeah, all of that works. I have 3 more appendices I quickly want to show you. Appendix number 1 is about another Boost library which you might want to have a look at if you are interested in using this design pattern in code. There's another Boost library called Boost.Functional Factory. That is the Boost library for those who want to use the factory method pattern in C++. Have a look if that is something you're interested in. I have another appendix where I'm trying to show you how these types std.function and Boost type erasure any actually work. So if you don't want to browse the implementation of Boost type erasure any in the Boost library, which is of course extremely complicated, have a look at the appendix 2. So there's a very simple primitive implementation to see what is actually going on in std.function and in Boost type erasure any. And there's an appendix 3. If you think there wasn't enough Boost at this conference and there wasn't enough Boost in this talk, there are actually 3 trainings lined up. I will be here in a month again in Berlin for a training on the Boost libraries. This is a training for German speakers only. So if you don't know German or if you don't plan to learn German until December, don't sign up for the first talk. There are 2 other trainings which I will give in January and in March. These are trainings which are all about Boost, so if you need more Boost, maybe that's an option for you. Thank you very much. We are at the end of the talk. I don't know how much time we have, whether we have still some time for some questions, so that's a pity. Then it means I might embarrass myself. So that's your chance to ask questions, and otherwise, thanks and enjoy the final keynote later.